So in section 3.4, we talk about the mean value theorem. This is the third of our value theorems. We've talked about intermediate value theorem in chapter 1, the extreme value theorem in the last section or two perhaps, and this is the last one, the mean value theorem. This is one of the most important theorems that we learn in calculus. Although we don't prove it here, we use it to prove lots of things going forward in other calculus classes and in analysis, so it's very important. And it says that if f is a differentiable function on the interval from a to b, then there is some c in that interval such that f prime of c is equal to f of b minus f of a over b minus a. So let's talk about what this means. First of all, let's look at this quotient here on the right-hand side of the equation. F of b minus f of a over b minus a should look familiar. This is the slope formula. So this is the slope of the secant line connecting the points on the curve when x is equal to a and when x is equal to b. So this is the slope of the secant line. Secant line connecting the point a, f of a, to the point b, f of b. And of course we know that f prime of c, the derivative, is telling you the derivative of the function at c. And that represents the instantaneous rate of change, or the slope of the tangent line at c. Okay, so what this theorem is telling us is that if your function's differentiable on this interval between a and b, then you can look at the average rate of change, that's the slope of the secant line, and you can know that there's some x value in that interval, we call that x value c, such that the slope of the tangent line is equal to the slope of the secant line. So let's draw a picture of that. Okay, so here's our function f. It's differentiable, it looks like it's differentiable everywhere, but we're really only looking at the interval from a to b, the closed interval. This is a nice smooth function. We can see that it's going to be differentiable. The mean value theorem tells us that if we take the slope of the secant line that connects the endpoints of this interval, so let me just draw that in here, make it nice and straight. Here's f of a, f of b. Okay, here's the slope of the secant line connecting those 2 points. Mean value theorem is telling us that you can find a value c in between a and b so that the slope of the tangent line is equal to the slope of the secant line. In other words, it's going to be a parallel tangent line to the secant line. And we can sort of take a guess at where that would be, just sort of based on the graph and what secant lines look like. Maybe it would be somewhere around here, where the tangent line has the same slope as the secant line, right? They're parallel to each other because they have the same slope. Mean value theorem guarantees the existence of such a point where the slope of the tangent line is equal to the slope of the secant line. Now, this is really kind of an obvious thing if you think about what this statement is actually saying. So I'm going to give you an example that goes back to our first example of how we talked about derivatives. So suppose that you traveled 140 miles over the course of 2 hours. Maybe you're on the Mass Pike and they clocked you at a particular point, and then 2 hours later they clocked you at the next checkpoint that's 140 miles away. Right? So what that means is that over the course of those 2 hours, your average speed, or your average rate of change, was, well, you traveled 140 miles in 2 hours, so your average speed would be 70 miles per hour. Does that mean you traveled 70 miles per hour the whole time? No, right? You could have been going 75 sometimes, you could have been going 65 sometimes, maybe you even went pretty slow at one point and really fast at another point, but it averaged out to 70 miles per hour. Well, the mean value theorem, which I'm going to abbreviate as MVT, tells us that at some point during those 2 hours, you traveled at exactly 60 miles per hour. Oh, sorry, 70. Average speed was 70. At exactly 70 miles per hour. your instantaneous rate of change, your instantaneous speed was 70 miles per hour, right? As opposed to your average rate of change or your average speed. And this makes sense, right? Yeah, maybe you went 70 miles per hour exactly the entire time, but probably not. More likely you were going 65 for a little while and then you sped up to 75 and maybe you came back down again. But the point is, if you were to go from anything below 65 miles or anything below 70 miles per hour to something above 70 miles per hour, you had to have passed through at one instant in time, a point in time where you were going exactly 70 miles per hour. Okay, which makes perfect sense. So that's essentially what the mean value theorem is saying. Now for our purposes in this class, we're going to use mean value theorem to prove a very important test, something that we've already sort of talked about a little bit before, but we call it the increasing and decreasing test. It says that if the derivative of a function is positive on an interval, then we can conclude that the original function f is increasing on that interval. And on the other hand, if f prime is negative on an interval, then the original function is decreasing on that interval. And we can see this a little bit in a picture. If this is our function f, and we think about where is the derivative positive? Derivative represents slopes of tangent lines, so we're asking ourselves, where does a tangent line have positive slope? Well, here, if we draw on this tangent line, certainly it's positive. And we start moving our point and looking at other tangent lines, they're going to keep being positive and keep being positive and keep being positive. Now, our lines are getting a little bit less steep as we go, which means they're maybe a little bit smaller, but they're still positive until we get to the very peak of this curve here, at which point our tangent line has a slope of 0. And so for this entire section of the curve here, the derivatives were positive. The slopes of the tangent lines were positive, and notice that the function was increasing. It was going uphill from left to right. Okay? Then what happens after? Well, between -3 and -1, now that we've passed this peak, our tangent lines have negative slope, right? If we draw on these lines, the slopes of these lines are negative. They're going downhill. And they're going to continue to be negative and continue to be negative, right, until we get to this point right here where they get back to 0. We'll notice that the slopes of the tangent lines, or the derivative, was negative for this entire interval, which is exactly where our original function f was decreasing. Then after that point again, if we start drawing in our tangent lines are going to continue to have positive slopes after that. So from -1 to infinity, our function is increasing, and the slopes of our tangent lines, in other words, our derivatives, were positive. So we could say, for instance, if I wanted to talk about the entire domain of the function, I'm just going to break up a real number line to describe what's going on here. From -infinity all the way up to -3, so from -infinity to -3, the derivatives were positive, and the function itself was increasing. It was going uphill from left to right. Then between -3 and -1, the derivatives were negative, right? The slopes of the tangent line were less than 0, they were negative, and the original function itself was decreasing. Then finally, from -1 to infinity, the slopes of the tangent line were positive, so f prime was positive, greater than 0, and your original function f was increasing again. So the increasing and decreasing test tells us that if we can figure out where our derivative is positive or negative, then that'll tell us where our original function is increasing and decreasing. And this can be really useful when we're trying to graph different types of functions. So let's look at an example. We're going to try to determine where this function, this is a, cubic, quartic function, it's to the 4th power, 3x to the 4th minus 4x cubed minus 12x squared plus 5 is increasing and decreasing. And I walk you through the steps on this one here. So the first thing that we're going to want to do is we're going to want to find the critical points. Now remember, in general, the critical points are the places where the derivative is either equal to 0 or the derivative is undefined, but the original function is defined. Now since f is a polynomial, that means both f and f prime are defined everywhere. So all we need to worry about for this problem in finding the critical points is figuring out where is f prime of x equal to 0. That's the only place we'll have a critical point for a polynomial function. All right, so let's go through it. We take the derivative. Here's our original function, so the derivative would be 12x cubed minus 4 times 3 is 12x squared minus 12 times 2 is 24, x to the 1, and this last term goes away. So we take that derivative, we set it equal to 0, and solve for x. Now how do you solve a cubic function that's set equal to 0? Luckily for us, there's no constant term. There's x's in every one of these terms, so we can factor out an x first. And it might actually be helpful not just to factor out an x, but to factor out a 12x, since that's our common factor. So I'm going to factor out a 12x, and I'll be left with x squared minus x minus 2 is equal to 0. What I have left inside the parentheses, I can factor even further. So this factors to, let's see, we'll have a 2 and a 1, x minus 2 and x plus 1. Make sure I did that right. Multiplies to negative 2 and adds up to negative 1, good. And so this function has 3 zeros, right? Here, here, and here. We set each one of these equal to 0 and solve, so we get critical points at if 12x is equal to 0, then that means x is equal to 0. X plus 1 equals 0 gives us x equals negative 1. And x minus 2 equals 0 gives us x equals 2. So this function has 3 critical points. All right, step 2 is to break up the real number line based on those points. So I'm going to draw my real number line. And I'm going to place those 3 critical points here. Now it doesn't have to be exactly to scale. I want to give myself enough space to do work on this number line. So I'm going to put, well, we should put negative 1 first, then 0, then 2. Right, so we placed our 3 critical points. And this, notice that this naturally breaks up the real number line into 1, 2, 3, 4 different intervals. Namely, the interval from negative infinity to negative 1, from negative 1 to 0, from 0 to 2, and from 2 to 4. The reason that I'm doing this is that I know in the end, these are going to be my increasing and decreasing intervals. I just don't know which is which yet. But those critical points are going to tell you exactly where your increasing and decreasing intervals will be. Okay. Once we do that, we move on to step 3. Step 3 says on each of the intervals that you've drawn up above, f is either going to be increasing on that entire interval or it's going to be decreasing on that entire interval. And remember what the increasing and decreasing test told us. It told us that if the derivative was positive on an interval, then your original function f is increasing. And if the derivative was negative on an interval, then your original function is decreasing. So what we're going to do is we're going to test a point within each one of these 4 intervals, and we're going to plug them into the derivative function to see if they're positive or negative. That information is enough to tell us whether your original function is increasing or decreasing. So let me be clear here, just down below, I'm going to test points in the f prime of x function to see if it's positive or negative. And I'm going to keep track of that down here. Afterwards, that's going to tell me where my original function f is increasing or decreasing. This is just how I keep track of the information. You can keep track of it in a different way, but I just want to make sure that we're clear that we're testing whether the derivative is positive or negative, and that's going to tell us whether the original function is increasing or decreasing. So this is what we do. We take a point in each one of these intervals and plug it into the derivative function. Now our derivative function was this thing right here, but plugging stuff into this and evaluating it is going to be kind of a lot of work. And remember that I only care about the sign, right, positive or negative of the outcome. So it's actually easier to plug in points into the factored version because it's going to be a quicker check to see if your outcome is positive or negative. So I'm using this factored version right here to test my points to see if they are positive or negative when I plug them into the derivative. All right, so let's do that here. We start with this first interval from negative infinity to negative 1. Don't choose the endpoint, since we know plugging the endpoint will give you 0. Choose a point inside this interval, something like negative 2. So I'm going to find f prime of negative 2 by plugging negative 2 into this function here. I'll get 12 times negative 2 times negative 2 plus 1 times negative 2 minus 2. And again, I do not care about the actual output, I just care if it's negative or positive. So this first term here is going to be negative. Negative 2 minus plus 1 is still negative, and negative 2 minus 2 is negative as well. A negative times a negative times a negative is negative. So now I know on this entire interval from negative infinity to negative 1, your derivative is negative. Okay, now let's repeat that in our next interval. This one's a little bit harder. I have to plug in an x value between negative 1 and 0. So you're going to have to choose some sort of a non-integer number like negative 1/2. So let's plug in f prime of negative 1/2. Again, plug it into the derivative function, the factored version. We'll get 12 times negative 1/2 times negative 1/2 plus 1 times negative 1/2 minus 2. All right, this first part here is a positive times a negative, that's negative. The second term is negative 1/2 plus 1, that's positive. And the last term is negative 1/2 minus 2, which is negative. So on the second interval, we have a negative times a positive times a negative, which overall is giving you something positive. So on this entire second interval between negative 1 and 0, your function is positive. Your derivative function is positive. Let's go back to our next interval from 0 to 2. Choose a point within that interval to test. I'm going to choose f prime of 1, right, positive 1. I plug it in here and I get 12 times 1 times 1 plus 1 times 1 minus 2. This is a positive times a positive times a negative. A positive times a positive times a negative is going to give you something negative in the end. So on this third interval from 0 to 2, the derivative is negative. And last but not least, whoops, I don't know why I wrote 2 to 4 here. This should have said 2 to infinity. It's a little silly. Okay, so choose some number between 2 and infinity. Let's say 3. I'm going to plug 3 into the derivative function, and I'll get 12 times 3 plus 1 times 3 minus 2. This is a positive times a positive times a positive. So on this last interval, I'm positive. Right? This is what the increasing and decreasing test looks like. Breaking up your real number line using the critical points, and then testing a point within each interval by plugging it into the derivative function and checking whether it's positive or negative. Now remember, anytime the derivative is negative, we know that the original function is decreasing, right? Think about both of them as going down, right? Negative is down and the function's decreasing. On the second interval, your derivative function's positive, right? Positive means up, so your original function is increasing. On the third interval, the derivative function is negative, it's down, so your original function is decreasing. And on the last interval, the derivative is positive, so your original function is increasing. And this is nice because this is telling you the general shape of your graph, right? It's saying that if you think about your original function f, it's going to be something that looks roughly like this, going downhill, then uphill, then downhill, then uphill. So it's going to be sort of roughly W-shaped graph. And we know all of this from the increasing and decreasing test. Right now, it's maybe worth being really clear and saying exactly what your increasing and decreasing intervals are. So f is increasing on the intervals, right? It's negative 1 to 0, union 2 to infinity, and f is decreasing on negative infinity to negative 1, union 0 to 2. Right, and the rough shape of the graph is something like this. I don't know where the x and the y-axis are relative to this graph, but this is just the rough shape given what we know from the increasing and decreasing test. Now notice that at this point here where we switch from decreasing to increasing, it looks like we're going to have a local minimum. Similarly here where we switch from increasing to decreasing, it looks like a local max. And here where we switch from decreasing to increasing, it looks like a local min again. We're going to formalize this in the next video when we talk about the first derivative test.